In the last video, we stumbled across this mysterious formula presented without proof called Gauss's Law. It looks enticing, but we're not sure how to use it just yet. So instead of just beating around the bush, I thought it'd be helpful to dive right into a few examples. For our first example, imagine we have this conducting spherical shell here with charge Q and radius capital R. What is the magnitude of the electric field at point P, which is a radial distance lowercase r from the center of the sphere? So we're asked to find the electric field due to a sphere of charge, which is a charged object. One option is to write out an integral for the electric field at this point by integrating tiny amounts of charge dq throughout the sphere. It is doable, but we pretty much need an integral in at least 2 dimensions, in some cases 3 dimensions, and I don't know about you, but me personally, I would much rather not solve a multiple integral if I don't have to. So is there an alternative to doing all that? Yes, there is. Gauss's law is our alternative. We know that the electric flux through a closed surface is completely determined for us, provided we know the charge inside of the surface, via Gauss's law. So what do we use for our closed surface here? Is it the outer surface of the sphere itself? I say no, that's not a good idea. The reason why is we could evaluate Gauss's law at the outer surface of the sphere here, but that would only involve information about the electric field at the outer surface, since only the electric field here is directly related to the flux going out of this surface. But we don't care about the electric field there. We only care about the electric field at point P. So what if we just imagine a sphere that surrounds this inner sphere? We imagine the second sphere such that it touches the point P, and it's still centered about the origin of the first sphere. Now we can apply Gauss's law to this imaginary new sphere instead of the original one. This might seem kind of weird and strange to you, but Gauss's law refers to any closed surface. It makes no requirements on whether or not the surface actually needs to exist in real life. So using this imaginary new surface we've created is not off the cards at all. Now, all we have to do is evaluate the flux through this imaginary surface, and that's equal to the charge enclosed over epsilon naught, no matter what the surface is. But we're now going to make an assumption about the behavior of the electric field. If this new imaginary sphere is centered about the same center of the original sphere, then the electric field vector through all points of this new sphere has the same magnitude and is always perpendicular to the surface. This follows just by the symmetry of the situation. Everything is symmetric about the center of the original sphere, so we expect that symmetry to hold, since rotating either of the spheres in any way should not change the field distribution at all, since the spheres themselves aren't actually changing when we rotate them. A rotated sphere is indistinguishable from the original sphere. That's also why it's really advantageous to choose a sphere centered about this original sphere. If we chose a different kind of sphere, for instance, even still touching P, but not taking advantage of the symmetry of the situation, then we would be in a lot of trouble, since we would actually have to evaluate the integral for Gauss's law, since the electric field has a different magnitude depending on where along the gray Gaussian surface you are. But now E always points in the direction of dA, so we can just write this as the magnitude of E times the magnitude of dA. Also, E has the same magnitude across the entire surface, so we can simplify this integral even further. E doesn't depend on the dA we choose, it has the same magnitude no matter what, so it's technically a constant in this integral. And boom, all we're left with is the closed surface integral of dA, or just A, the total surface area of the sphere. And the total surface area of a sphere is 4 times pi times the radius of the gray sphere squared. So Gauss's law here implies E times 4 pi r squared equals Q enclosed over epsilon naught. Solving for E is as simple as dividing by the surface area, and we're left with this peculiar expression here. Remember that Coulomb's constant K is equal to 1 over 4 pi epsilon naught. So we end up with kq over r squared. This looks exactly like the electric field due to a single point charge. It turns out that a uniform spherical distribution of charge like this one here produces exactly the same electric field at an external point that a point charge would with the same amount of charge. Pretty cool. Keep in mind here that little r is not the radius of the sphere. Remember, we called that capital R in the beginning. Little r is the radius of the gray Gaussian surface, or the distance from the center of the charged sphere to point P. For our second example, consider a thin and infinitely long line of charge with linear charge density lambda. What is the electric field at P, a radial distance r away from the line? Now, this is something we could actually feasibly do by solving an integral. In fact, it was one of the problems in the previous module, and if you remember how difficult it was, you'll be pleased to know we can sidestep all of that difficulty and use Gauss's law to make our lives way easier. It only makes sense to use Gauss's law here if there's some sense of symmetry that we can take advantage of. So if the line is truly infinitely long, then we expect the electric field to point radially away from the line by symmetry. The reason why is, for every dq on one half of the line, you can choose a symmetric dq on the other half such that the sum of their electric fields points straight up, like here. Summing over all of these dq's then, we expect the electric field to point radially away. And actually then, because the line is infinite, the electric field everywhere points radially away from the line by the same argument we've just made here. It feels a bit counterintuitive, but that's infinity for you. Infinity is weird. In that case, a smart choice for our Gaussian surface would be an imaginary cylinder of length L, which surrounds a portion of the line of charge and slices through this point P. What makes this a smart choice is it takes advantage of the radial symmetry of the situation. Then the electric flux through this closed surface is made up of 3 parts: each end of the cylinder and the tube part. Since each end of the cylinder is parallel to the electric field, the flux through each of the ends is actually 0. Another way of looking at it is the electric field makes a 90-degree angle with the area vector of each end. So the only real source of flux is not at the ends, but along the tube-like part. The electric field along the tube has a constant magnitude and always points in the same direction as the dA vector. So evaluating Gauss's law here gives us EA equals Q enclosed over epsilon naught. Now we just have to figure out what is Q enclosed and what is A. Q enclosed is just the charge enclosed by this imaginary cylinder, or just the length of the cylinder multiplied by the linear charge density, lambda. A is just 2 pi RL, where R is the radius of the cylinder and L is the length. To see why this is, imagine if you could unwrap this cylinder into a rectangle. That rectangle would have a length L, same as the cylinder, and a height C, the circumference of the cylinder, which is pi times the diameter, or 2 pi r. And so the area is the circumference times the length, or 2 pi r times L. The rest is just rearranging, and we end up with our final result of lambda over 2 pi epsilon naught r, where r is the radial distance from the center line to the point we care about. These were just a couple of examples for us to get our feet wet with Gauss's law, and there are actually a bunch more in the exercises and problems.